So last time we were talking about the shape properties that we have in the steel book, the steel manual. And we were talking about the W shapes. It stands for wide flange. The flange here is kind of wider when you compare it with the S shapes, the standard I-beam. So if you compare, let's say, with the same depth, the same weight, you'll find out that usually this width here is larger than the width for the S shapes, for the standard shapes. Also, the M shapes is going to be miscellaneous, and as you see here, it's going to be very skinny, and the aspect ratio is really large when you compare D to B, when you compare it here to the S versus the W, right? And then we have the HP. Usually the HP shapes, this is for the H, they look like an H and used for piles, and usually the depth is very close to the width. We have the channels, it's like C shape, as you call it. And then we have also the miscellaneous channels, it's kind of lighter. This is a very famous section that we use for stairs. Otherwise, we use W12 by 20.7, 25, or 30. We have the angles. Sometimes we have equal angles. Sometimes we have unequal angles. So when it says here equal versus unequal, it's going to be about the leg. So for example, here's the L, means it's going to be an angle. 8 by 8 means the length of this leg is going to be 8 inches, and the length of the other leg is going to be also 8 inches. And the thickness here is 1 1/8 of an inch, which means the thickness here. And the thickness here is going to be the same as the thickness here. Even if the angle, if we have an equal angle, which means let's say 4 by 6 is going to be an equal length for both legs, thickness is going to be the same. It cannot be different. What you have here in the table is going to be the K distance. This is where we have this round shape. We have the weight as in pound per linear foot. We have the cross-section area. We have the moment of inertia about the x axis. Here's x, here's the y. So we have moment of inertia, section modulus, and then we have R, which is radius of gyration. We have also the y bar. Y bar is going to be the distance from the bottom of the angle to the CG of the angle. We have the Z, the plastic modulus. We have YP, which means distance is a plastic modulus. And then we have some flexure torsional properties that we don't really need in here. So I'm gonna skip this part here of the table. WT shapes is gonna be like a T shape, but it's taken as part of the W shape. This is why we call it wide flange T shape. So actually, if you think about it, it's gonna be like as if you take a W section and then you cut a piece of it, and then you call it here WT. These W shapes are very useful when you have drops in buildings. They are also useful if you like to do a retrofit. So if you like to retrofit an existing beam, steel beam, you'd usually either add a plate on the top or bottom flange, or you can add a WT section. WT section is going to give you very high moment of inertia when you compare it to a steel plate. Because you imagine if you add here this WT above or below a steel section. You're as if you are putting a plate here, but you put it further away from the flange of the original beam. And with that, you gain lots of moment of inertia and section modulus. For the WT shape, yes, go ahead.
Sir, what is WT shape used for?
It is used to retrofit beams, and we're going to see this later on. And also used in drops. When you have a drop in a building, like a step, so this is going to be very useful.
Okay.
We're going to be showing you some details about this. Information here available is going to be very similar to the one that we have seen in the W shapes. We have the cross-section area, we have the depth. As you see here, we have the depth is going to be for the analysis, for the design or calculation. And this column here is going to be for detailing. If you like to develop a drawing, this is going to be the depth that you need to use. As you see here, 3/4 of an inch is not 0.8, right? So to be accurate is 0.8, but if you like to show it in a drawing, or you'd like to use it in your detailing, you're going to be using 21 3/4 of an inch. You have some information about the stem, like the thickness of the web. We have some stuff about the flange, and then we have some K value that you'll need in detailing. You don't really need it in analysis, but you need it more in detailing for now. We have this rectangular hollow steel sections. It could be also square. like what you see here, square HSS. As you see here, it's called HSS 20, which means this distance from here to there is going to be 20 inches. And the width here is going to be 12 inches. The wall thickness here is 5/8 of an inch for both sides, for here, for the top, and for the side. So the thickness usually is going to be uniform throughout the entire HSS. As you see here, here's the exact thickness of the wall, 0.58. It is not really 5/8 of an inch. And look at this, 1/2 inch, but the exact one, if you like to do some analysis, is going to be 0.465, not really 1/2 inch. Here's the weight as in pound per linear foot, cross-section area, and then you have this B over T, which means the width divided by the thickness. This is going to be very useful information. Later on, you'll need it. When you design this as a brace, you need this value B over T and H over T. About the x-axis, you have moment of inertia, section modulus, the rate of gyration, and Z, which is the plastic section modulus. We have the same thing about the y-axis. If you have a square, properties around the x-axis and y-axis would be the same, like what we have here. Around the x and y, if you see here, you see I and S and R and Z, and it does not mention whether it's going to be for x or y because they're the same. But in here, it is mentioned for x-axis. On the other page, which is opposite to this one in the book, you're going to see properties for the y-axis. For a square, you don't have that because they're the same. They're identical about the x-axis and the y-y. We have also round HSS. And this round HSS, they're different from the standard pipe. Okay? Let me tell you the difference between the two. In the HSS round, as it says here, 20.000 by 0.5. Wall thickness, 465 inches. The outside diameter is exactly 20 inches. The outside diameter here is going to be exactly 18 inch. Outside diameter here is going to be exactly 16 inch. And then after that, you have all the properties for that section. All right? Including the weight, the thickness, cross-section area, moment of inertia, and the entire thing. When you go here to the standard pipe, it's going to be different. If you look here at this pipe, 12 inch standard. Look at the outside diameter. Look at the inside diameter. Look here at the standard end, the standard 10-inch pipe. Now let's jump here to a complete different one because here you're going to say, yeah, this is usually for the inside diameter. Look at the 8-inch, 863. Look at the inside diameter, 798. It is not really 8-inch. So where's the 8-inch? Somewhere in the middle. Same thing for the 6-inch. I was thinking here that if this 8 inches, inside diameter is going to be a little bit shy than 8, and the outside diameter is going to be 8.63. So I said usually this thickness here, or this diameter, is going to be in the middle, but look at this. For the 6-inch, it's not. Look at this, it is not. Look at the 1.5 inch. 1.5 inch standard pipe diameter. Look at this. It's going to be 1.9. And the inside is going to be 1.6. So it is not really 1.5 inch. To continue here with the standard pipe, so as it says here, this is going to be pipe standard. We call this also Schedule 40. This term here is used for hydraulic design. So the name or the term Schedule 40 is coming from hydraulic design, from mechanical engineers or civil engineers when you do pipeline design. We have another set of pipes. We call it extra strong. You see this extra strong, extra strong. Extra strong, this is what we call here Schedule 80. It's like stronger pipes. They have the same label here. It's going to be pipe 12 inch, 10 inch, let's say 3 inch. So let me here pick on this 3 inch pipe. Let me see what's happening there. In the 3 inch pipe, look at the thickness, 0.3. Look here at the 3 inch in the standard, 216. So this is going to be like thicker pipe. So it's going to be stronger. So it can take higher pressure. And also it's going to be taking high axial force. Because usually these pipelines, or these pipes, excuse me, The pipe sections, we use them for columns. Also, we use them for braces. And trusses, we can use them for braces. We have XX strong. This is now stronger. If you remember the 3-inch pipe, it was 0.216 in the standard, 0.3 in the X strong, and the XX strong, look at this. This is gonna be 0.6. It's so strong. This is gonna be expensive. You don't try to use it. If you're doing an actual design, stay away from the XX strong, and also stay away from the X strong. Try to use the standard as much as you can, because of availability and also because of the price. Any questions? We're good?
All good.
All right. All right. Also in the steel book, we have properties for 2 angles back to back with some distance between them. The reason we have this because in many cases we use this as a brace in trusses. So as a truss member, you can use 2 angles back to back. So the question is, do you need to bring 1 angle and then say, I'm gonna be doubling it? How about the moment of inertia around the YY and the moment of inertia around the XX and those kind of things and the total cross-section area? So they'd like to make it easier for you because it's like a design aid. So what they have done here, they have 2 angles, 8 by 8 by 1 and 1, 1/8 inch. Here's the cross-section area, and then you have the radius of gyration, and then you have lots of other information.
Sir, instead of double angles, why don't we just use WT sections?
The what? What don't we use what?
WT section.
The WT? Because right in the
Yes.
middle here, right in the middle, you can put a plate, a gusset plate. So you can attach these 2 angles to a plate in the middle. We're going to be going through some examples, and you're going to see a detail that shows the reason that we have these 2 angles. Because at the end of this member, of the brace, you can put a steel plate, and the steel plate is going to have a thickness of S. And you look at this separation S, it can be 0, 3/8 inch, and 3/4 inch. And once you put the plate in here, it's going to be controlling the moment of inertia about the YY axis. Right? If this makes sense, because you put them further away from each other or you bring them closer to each other. Same thing for the double angle. This is going to be the extension of the table on the other side. Also, you can have 2 channels. Also, 2 channels, you can use them for brace members, like for trusses, big trusses, for bridges, for steel bridges, you can use them. And you have the properties for combined sections, the same thing, with an S distance between the 2. Also, we have plates. We call this a checker plate. You see, this is a checker plate. I'm sure that you guys have seen it. You can see here the gauge and the weight. And you see here the thickness and the weight. Thickness, the weight. So for each, let's say that you're looking for 1/4 inch plate. You know the weight is going to be 11.3. It's okay if you like to figure out the weight based on the unit weight of the steel. Anyone knows the unit weight of the steel? How much is the unit weight for steel, structure steel, or any steel?
$7.85 ton per cubic meter.
Okay, but I'm looking for pound per cubic foot. It's going to be 490 pound per cubic foot. So if I'd like to figure out the weight of a plate, like a square foot of a plate, you take the thickness, let's say 1/4 inch, you divide this by 12 to put it in feet. And this is going to be the thickness. This is now 1 dimension. And then you have the X and Y is going to be equal to a foot. So you take 1/4 divided by 12 times 490. The number is going to be very close from this number here. So you can either use this, which should be a little bit heavier than the analysis, because this deformation that you see here. We have also this combined shape. Sometimes we have this W section with a channel. The reason is because we use it in industrial buildings when you have a crane. So if you have a crane, the rail is going to be right on the top. The forces applied to the crane beam is going to be vertical load. That's why you have the W section. Also, you have lateral shock. This lateral shock is going to be coming from the brake and from the shaking of the crane. So to take this lateral shock or this lateral force, you need to have a channel. So the reason that we have the channel here is going to be helping with the lateral shock. So it's going to be bracing the top of the beam. Since this is going to be used widely in industrial buildings, the structural steel book here includes this combined section with all the properties. And the very famous and common combinations, as you see here, is going to be this MC with this C, right? It's going to be this W section with either this or that. This W section with this or this. And then they give you all the properties just to make it easier for you. So this total weight is going to be for both sections. It's going to be for the W section and the MC, 18 by 42.7. When you add them, it's going to be this number here. They call this a cap channel. This to continue with the same table. Also, we have the railing. You see this rail for the crane rail. We have the EGCE, and the very common one is going to be EGCE 40. This is going to be the very common one that is used widely in cranes and construction to use this guy here, EGCE 40. This is going to be the section designation. And of course, here you have the weight, you have the information about it, moment of inertia, and all of the stuff you're looking for. All right. So now we need to talk about the ASTM when it comes to structural steel. We have in this table 1.1. If you look at the book, it's going to be table 2.3. So I want to show you some stuff that you're going to see there. Do you guys see the table number on the top?
Yes.
If you have a structure shape like W section, like S section, and so forth, in the steel book here, you have this table that includes all the STM designation and the available sections for it. For example, here's the W section, M section, S, the HP, the C, the MC, and the L, and then you have the HSS, the rectangular round, and then you have the standard pipe. So let's say you'd like to design a W section. What ASTM number that you need to specify in your drawings? This is going to be the question. And then you have here three options at the bottom of the table. It says here preferred material specifications. It's going to be other applicable materials specifications, but it means most likely you're not going to see it in the market. And if it is just light, like empty, it means it doesn't happen. For example, I'm looking here for W section. What section should I use? What ASTM number I need to use nowadays? It's going to be ASTM A992. Look for the yield strength, it's going to be right there. Looking for the ultimate strength, it's going to be right here. Now I'm looking for rectangular HSS, like HSS 4x4 by quarter of an inch. Now which ASTM I'm going to be working with, which properties I need to consider in my design. I'm going to say it's going to be A500, grade B 46. This is going to be the one. All right. Let me look closer. So this is the same table, just zoomed in. This is going to be the common section that I'm going to be using in my design and practice and in this course. If you have a W section, look at this dark shaded cell. It means for W section, I'm going to have ASTM A992. Yield strength is going to be 50. I'm not going to be using 65. Ultimate is going to be 65. Good. Next section. If we are using M or S or C channel or miscellaneous channel, run an angle, go with A36. You read the trends here, it's going to be 36, and the ultimate is going to be 58. Don't use 80. It's going to be just 58. This is the number that you need to use. If you have a standard pipe, don't use it or don't consider it to be A36. It's going to be something called A53 grade B with yield trends of 53, 35, and ultimate trends of 60. We went through the HSS rectangular, which is very common. The A592 is kind of a replacement to the A992. As you see here, 529 replacement to the 992. In some cases, you specify or you order A992 steel section, and the suppliers can say, we have 529 instead. Is this okay? And certainly you can say, yes, it's okay. I can take it as a replacement to the W section. In moment frames and eccentric brace frames, in lots of cases, we'd like to use angles made out of grade 50. I don't want to use this grade 36. So in a case like this, I'm going to specifying here A529 grade 50 angle and channel and this kind of things. How about plates and bars? Because plates and bars, if you look here, this is going to be for the standard sections, like rolled up sections. Rolled up means like W, M, S, HP, and C, and this kind of things. Just for plates, it's going to be all A36. If the plate thickness start from, let's say, 1/8 of an inch, all the way to 8 inches, you can use it as A36. If sub Y is going to be 36, and if sub U is going to be 58. Once you go above 8 inches, which I've never used or seen, is going to be, if sub Y is going to be 32 KSI. Just for information here. So we have material properties for all this rolled up sections, and we have it also for plates. The other thing also that we need to look at is going to be for the fasteners. Fastener means bolts and all threads and this kind of things. We have here all designation. So we have the very famous one that we call here A307. A307, which is machine bolts, like in here. This one, let me stay here. It's going to be like machine bolts. We have also the A36. A36 is used for just threaded rods, like an old thread. We call this old thread. A325 is going to be high strength bolts. Now, I'm not expecting that you're going to be memorizing all of this information for now, but if you like to take note, this would be great. Otherwise, you wait for the connection section that we're going to be covering, and you're going to see the use of all of them. So if you're looking here for high strength bolts, it's going to be A325 and A490. Here's the ultimate strength. There is no yield strength for it because you don't really need it when it comes to the shear strength and tensile strength of this high strength bolts. If you are planning here to use, look at this, threaded rods, like an old thread, is going to be A36. If you are doing here common bolts, we call this common bolts or machine bolts, this is going to be A307, grade A. This is going to be very common. This is like the cheap bolts that you can buy. A449 is also used for threaded rods. And here's the trends for them. The one that's really available these days, if you like to order, if you like to specify, is going to be the threaded rods, which is F1554. We have 3 grades. This is going to be the lowest grade. It's going to be like the A36, very similar to the A36, but we call this F1554, which means in the drawing, if you specify F1554, grade 36 is going to be the same as if you specified here A36. You can put either one of them, and supplier can get you either one of them. They should be fine. Also, you have the grade 55 and the grade 105. If you have like foundation of a moment frame, definitely you'd like to use maybe something like this. High strength bolts or anchor rods, old threads. All right, for the steel framing. Now we need to talk a little bit about the steel framing. What's happening in there? In buildings. So usually you're going to see beams, you're going to see columns, you're going to see connections, you're going to see braces, and of course you're going to see here moment frames. Even when you do here wood and masonry construction and concrete construction, you're going to see some steel members slide. From time to time you're going to see it, you're going to see anchor bolts, you're going to see some braces and this kind of things. This is here a plan view that shows structural steel building. Actually, this is part of a mall. As you see here, each one of these lines represents a beam. Here's a section for this beam. It says W21 by 44. This is going to be the beam section. Nominal depth, as it says here, is going to be 21 inches. The weight is going to be 44 inches. This C means camber. Camber is something which is opposite to deflection. So beam deflects downwards, this camber, which means that the pre-bend this beam before they install it, and the amount of negative deflection, if you want to call it this way, the amount of camber here is going to be 1 inch. Reason that we have this camber, when we have excessive deflection in a beam, and this camber here is going to be eliminating the dead load deflection, which means once you install this beam and you put the concrete slab above it, the beam is going to be flat. As you see here, W18 by 35, there is no camber here. We don't need it here. In this case here, I need a 3/4 inch. And here, don't need any camber. Here, the camber is 3/4 inch. So I guess now it's clear why do we have this C equals right next to the beam size. Usually this indicates a column. So I have here a structural steel column, another column here, a column and a column here. I don't have a steel column. This round column is a concrete column. So this construction here is made out of, you have this combination. This round column is existing column. And as you see here, typical existing edge of concrete slab. We have existing construction that we're trying to add this to it. So we try it here to utilize this steel column. We're going to be attaching it to it. This rebars that you see here is going to be rebars for the metal deck. So when it comes here to this analysis, you say, do I need it? I'm going to say no. This for the diaphragm analysis, for the seismic analysis of diaphragm. So I guess the main elements that you see here is going to be a steel beam. Usually we just draw it as one line and it has certain spacing. This is going to be also a steel beam, like a girder. It's going to be a column, steel column. And when you have here a moment connection, we do this solid triangle this way. So this here seismic moment frame is going to be in this direction. So this solid triangle means that you have a moment connection here between this column and between this beam. This means a brace. Usually it's drawn this way. When you have one arrow, means it is going to be the low point of the brace. When you have two arrows, it's going to be the high end of the brace. It's going to be like a standard industry that we usually use. On the top of the steel beams here, we have a metal deck. It's going to be filled with concrete so that people can walk on the top of it. This is why we call here D1. Typical means everywhere. So I'm going to have here a metal deck on the top of the steel beams. Okay. We have an example. Yes.
What do you mean by a low point and high point in the bracing?
This brace here
is
used to brace the bottom of the steel beam.
Oh, so in terms of location on the beam?
Yes.
Okay.
So this here means the top of this beam. It goes to the top of the beam right below the deck. I'm going to show you quick pictures here. It's going to be coming very soon. Like here, for example. This is going to be the top of the beam, the bottom of the beam. So what you're trying to do in the previous slide, you're trying to brace the bottom. So the side that shows only one arrow is going to be the bottom of the beam. The side that shows two arrows is going to be the top of the other beam next to it. Now let's go back. Which means this point here is going to be the bottom of the beam, right? Of this beam. And this point here is going to be the top of this beam. So this brace here connects between the top of this beam to the bottom of this beam. Later on, I'm going to show you detail when we do seismic moment frame design. We'll figure this out in a good detail.
Okay, sounds good. Thanks.
But what I'm trying to say, this is going to be designation for a brace. And this is the way we show it on the plan. Comes to concrete deck above it, this designation is going to look like this. If you like to see a picture of it, it's going to be like here. Here's the metal deck. It's going to be attached on top of the beam. It's going to be filled with concrete so that you walk on the top. In this example here, we're trying to figure out the demand. If you remember what we talked about, the design philosophy for methodology, we said that we have two design methods. We have the ASD, allowable strength design, and LRFD, load resistance and factor design. So in the first step here, we need to figure out the loads. How do you do the loads here? It says a partial floor plan of an office building. Now, what's the importance of saying an office building? When you have an office, you can figure out the occupancy, life load. Occupancy life load for an office is 50 pounds per square foot. It is shown in figure 1.3. Dead load including the self weight of the metal deck, the steel beams, and all additional dead load is 85 pounds per square foot, PSF, which means the weight of all materials. Let me go to here. The weight of the steel beams, the braces, the metal deck, the concrete, whatever, any additional, you have flooring, you have some ducts below, you have some piping, total weight is going to be 85 pounds per square foot. The span of beam 1, this is going to be B1, is 33 feet. It says determine the design load for B1. Now, if I'm doing here any analysis in this course, it's going to be only LRFD. Are we good about this? So if I need to do any load combinations, if I need to use them, it's going to be usually LRFD. We are not going to be doing ASD. Now, which one is B1? And it says here figure 1.3. So let me move forward. It's going to be figure 1.3. It says here B1, and this is going to be also B1. The span, which means the distance from this point to that point, is how much? Anyone recalls the number?
33 feet.
33 feet, exactly. Now, it seemed that the beam size at the end is going to be W16 by something, right? But which one is going to be B1? I mean, they say just find out the design load for B1. So which one of them? Look at the spacing here. The spacing between this beam and between that beam is 10 feet and 3 inches. This spacing is 11.5. This spacing is going to be 9.7. So the final beam size of both of this B1 is going to be the same. But the question is, which one do you think is going to be supporting more load?
The one have larger tributary area?
Exactly, larger tributary width. So I need to figure this out. So looking at this beam or that beam, from this 11.5, it takes 1/2 of it up to this red line. The top one here takes 1/2 of 10.3. The bottom beam takes 1/2 of 9.7. So I'm going to be going with this. Tributary width for this beam, now this is going to be my B1, if you like. It's going to be 1/2 of the 11.5 plus 1/2 of the 10 and 3 inches, if this makes sense to you guys. So it's okay. Step number 1, figure out tributary width. Tributary width for this beam 1 is going to be 11 feet. This is not negative. This is going to be 11 feet and 5 inches plus 10 feet and 3 inches. You add them and then you divide by 2, which means you take 1/2 of this plus 1/2 of that. And with that, I have a width, tributary width of 10 feet and 10 inches. So, okay, good. Now, when I say here design load for B1, it means I'm looking for the load as in pound per linear foot or kip per linear foot of the beam length. If you have the uniform load here, multiplied by this width, can I get you here the load as in pound per linear foot or kip per linear foot of the length of this beam? I said, okay. Let me take here 10.83, which is the same as 1010. It's going to be 10.83 feet. This is going to be tributary width. Multiply here by uniform load as an 85 PSF for the dead load. With that, I'm going to have 921 pound per linear foot, or you can call it 0.921 kip per linear foot. In the structural steel, we'd like to keep everything almost as in kip and foot units. Otherwise, the number is going to be just very large. When you do wood design, you'd like to keep it as in pound and foot. When you do concrete, it's going to be kip and foot. In steel, it's going to be also kips and foot. Now, how about the life load? I'm going to say life load. Life load is going to be the same thing. As I said, you have an office building. Occupancy load for an office is going to be 15 pounds per square foot. But from time to time, you should be able to reduce it, because what is the potential, what is the probability that you're going to have this life load applied to every square foot of this tributary area? code says if the tributary area here is more than 150 square feet, you can have some reduction. So the question is, how much is tributary area for this beam? Tributary area means it's going to be 10.83 feet multiplied by 33 feet. So I'm going to go back here to the analysis. I'm going to say tributary area is going to be 10.83, tributary width multiplied by the beam span. It is more than 150 square feet. So I should be able to reduce the life load. I have an equation for the reduction. Here's the equation for the reduction. It says reduction factor equals 0.08 tributary area subtracting 150, because it says if tributary area is going to be more than 150 square feet, you should be able to use some reduction. Now, where is this coming from? It's going to be coming from the CBC, California Building Code. And here's the amount of reduction. It's going to be 16.16%. So reduction here is almost 16%. So the effective or the final reduced life load is going to be 84%. If you have 16%, it's going to be a reduction. It means the used life load is going to be 100 subtracting 16. This is exactly what I have here. So I'm going to have here 84% of that life load to be used in my analysis. Now my reduced life load is going to be 84% of the 50 is going to be 42 pounds per square foot. So I didn't want to use the 50 because I have here a chance to reduce it a little bit. The only reason that I'm able to reduce it because it's going to be occupancy load as in 50 PSF front office as given by the code. Now, which code specifies a 50 PSF? I'm going to say the code is going to be, of course, CBC, California Building Code. What exact code or standards that say that? I'm going to say this is going to be the EGCE 7, 2016. It says life load from office is going to be 50 pounds per square foot. When you go here to the CBC, you see here this reduction equation, and you can safely use it to take the life load from 50 to 42 because the tributary area here is going to be more than 150 square feet. Questions? Any questions?
No, all good.
You're good? Since we have Camber here, Camber, are you here? All right.
Yes, Professor.
Do you have a problem with the mic?
No, it's okay.
All right, great.
Yeah.
Very good. Thank you. All right. So I guess now with the step here, I was able to figure out uniform dead load as in capillary foot. Now I need to do the same thing for the life load. I was thinking just use 42 PSF. But the code says this is going to be an office occupancy. When you have an office, you need the partition weight. And the partition is going to be considered as life load. And you cannot reduce them. And they say use minimum of 15 PSF. So what I need to do is take the 42 and add 15 PSF to it and use it as life load. So this reduction here doesn't apply to the partition loads. So I'm going to say here 42 plus the 15 PSF for partitions. Now this is going to be my total life load multiplied by the same tributary width, very similar to what I have done here in the dead load. With that, I have 0.617 kip per linear foot. Now I have my dead load and I have my life load. What should I do next? I'm going to say load combinations. You look here for the design load. Design loads means the ultimate load, which means the demand load. I have two load combinations. If you guys recall, when you have dead load and life load, I have the first equation says 1.4 times dead. The other one says 1.2 dead plus 1.6 times life. If you look here, 1.4 times the dead load, 921 taken from here, right? Here's going to be the design load. Based on this equation, 1.29. Based on the second load combination, it's going to be 1.2 times the dead load plus 1.6 times the life taken from here. It's going to be 2.09 kip per linear foot. Now I need to take the larger of both of these two as it says here, 2.09. Of course, it's going to be larger than 1.29. So it says here that this value here controls, and this is what I'm going to be using in my analysis. Any questions?
Doctor, for the reduction of the live load, that formula you said that's from the CBC, right?
Yes, you can find it in the CBC.
Okay, thank you.
All right, no problem. Any other questions? All right. In the steel beams, we have steel beams that we call composite versus non-composite. So I need to understand the difference between the two. When you look here at this plan, it says that you have here a metal deck with concrete. If you remember this, you need to walk on the top of this. You need to have concrete. When you do your analysis to this concrete, to the steel beam with the concrete topping, with the steel deck and concrete topping, you need to attach between the two. So you're going to put this mechanical connectors. We call them studs. This mechanical connector here is going to be connecting between the steel beam to the concrete. So what these do, they bring this studs or mechanical connectors and they weld it to the steel beam through the metal deck, which means first, they put the steel beam in place. Second, they put the metal deck. Third, they bring the stud and the stud itself, while they are welding it to the steel beam, they're going to be cutting through the metal deck. They're going to be burning it. Now, this connector for the stud is going to be welded to the steel beam. After that, they bring the concrete and then they put it right here. Now, it's going to be a composite section. And why don't you consider the composite action? Composite action means the help of the concrete to take lots of the compression as long as the steel is going to be able to take the tension. So this is going to be very similar to what you do here in concrete design. In concrete design, you have a section with some reinforcement at the bottom, right? So this is going to be kind of similar to it. You have concrete and steel, they work together. So in this case, you can say, let me design this here as a composite section, not just as a steel beam. And this is something that you're going to be doing in this course. Now, the question is, what happens if I don't have good connection between the concrete and between the steel? If you don't have this concrete stud or metal stud, attach it to the concrete and to the steel beam and connect between the two, it means that you don't have any composite action. And in this case, if you want to design the beam, it's going to be just bare steel beam. You cannot consider the concrete contribution to the steel strength. If you have a roof construction, usually in the top of the roof of a building, you don't really put any concrete because in the top of the roof, no one is going to be walking in there. It's going to be only for maintenance of some equipment. So in a case like this, you don't really need to have concrete topping. You're just going to have some roofing. In a case like this, what you need to do is to just weld the metal deck to the steel beam. You can do puddle weld, or you can do shot pins. You can do like screws. You can do some mechanical fasteners and connect the metal deck to the steel beam. Now, in this case here, you don't have any composite action because there's no concrete. You just have some roofing material, like insulation and roofing and this kind of things, and waterproof material. So again, when it comes to beams, I may have composite, and they may have non-composite beams. Let's say that I have the same size of the beam. At one time, I have it with a concrete deck, and I have good connection between the two. In the other case, I don't have any concrete here on the top. Which one do you think is going to be stronger? Which one do you think first is going to have higher strength, which means higher moment capacity, number one? Which one is going to have higher moment of inertia, which means deflects less?
The composite one is going to be more stronger and must have more.
This is correct. And which one do you think is going to have higher moment of inertia?
Non-composite beam.
Actually, also the composite beam, which means with the concrete, moment of inertia is going to be larger, which means deflection is going to be less. So I'm expecting here, if I'm doing a design for a floor system and I have a composite system, I'm expecting that the beam size is not going to be as big as the same beam size that you would pick if you don't have this concrete topping or if you don't have this composite action. can give an example. Let's say I'm doing here a design, and I have been told that you have here this concrete deck, and they have Nelson studs or connectors, mechanical connectors between the beam to the concrete slab. I'm gonna run my analysis, and I find out that my beam section is W16 by 31, just a size. I'm throwing here a size. Now, if you like to take out these connections, these connectors here, and not use a composite action, I'm expecting, if you like to do the same design without these connectors, without the composite action, that the beam size is gonna be slightly larger than W16 by 31. Maybe W16 by 40, or maybe W18 by 35. It's gonna be larger in size. Because all of a sudden here, you lose the contribution of the concrete to the strength and to the stiffness or moment of inertia of the beam. So what do you expect? Of course, the beam is gonna be larger, if this makes sense to you. So this is why I have this example 1.2 about this concept. It says here, a structural steel fabricator received drawings signed and stamped by a civil engineer, which means it's already designed. The steel beam here says W16 by 31. It has metal deck. And of course, it has mechanical connectors, which means this is gonna be composite design, right? Now I have composite floor system, and they have the beam size. The contractor here found out that the middle third of the steel beam has an opening. What do you mean middle third of the steel beam has an opening? I'm gonna come here, I'm gonna say, let's say here in the middle third of the beam, when you look from the top, you have a big opening here, which means that you don't have concrete deck, which means that you lose here the composite action. And this opening here, we need it because we're gonna be putting a crane. You need to have a crane, and the crane is gonna be running through the slab. Let me go back here to the plan. I'm gonna be cutting here a section of the concrete. I'm not gonna provide at the beginning. I'm gonna be putting here a good sized crane that I need it right here, which means I'm gonna be losing here the effect of the composite action during construction phase. I don't have it. Later on, maybe I can put it back. I can put the concrete slab back. Now, what should I do? Which of the following statements is correct? As a contractor, what should I do? So I just do the cut, put the crane, and say everything is gonna be good? No, nothing was discussed about this. Here are the four options I have. It says here, should be fine as long as the concrete deck will be poured at the end of the project. You say, you know what? I can just do the cut here. I can do the hole. Later on, we're gonna cover it with concrete. Nothing is wrong with this. Answer B here says the engineer should provide a design for the beam to support the dead load and the construction life load. What's construction life load? It's gonna be different from an office load. So we need to figure out what construction life load we have in there. And during construction, you're not gonna have this composite action. This is gonna be the problem. During construction phase, you lose here the composite action. And also you have the crane support. You need to support the crane somehow. And the beam, most probably, is gonna be larger than the beam specified here, W16 by 31. I see, yeah, I mean, you'd like to do a change here. During construction, the engineer doesn't know that you're gonna put the crane there. So you need to go back to him and tell him, I'm gonna put here an opening. I'm gonna be losing the composite action. What do you wanna do about this? Do you wanna change the design of this beam? Item C here, it says the contractor should not put an opening in the deck. This is great. So what should I do now as a contractor? I need to have a crane. Otherwise, how would I move the material up and down? D, the engineer should provide a design for the beam to support dead load and the construction life load. And for sure, look at this for sure, the beam size will not change. Now, based on our discussion here, what do you guys think? I'd like to hear from all of you, not just one person. And give me some reasons for your answer. Hello?
Doctor, I'm confused between points B and D.
B and D?
Yes.
Okay. In B, I'm saying that the beam size is going to get changed. Most likely. In D, I'm saying for sure it will not change. It's going to be the same size.
Okay.
I feel like B is correct because I think during this stage, concrete hasn't poured yet. And if it's designed as a composite beam, it likely doesn't have the capacity that the engineer designed for it.
So there is no way, or I cannot say for sure the beam size is going to be the same. You don't feel that?
Yes.
Why?
Um,
You say the good reason here for item B, but I'd like here to see a good reason to reject D.
I guess it depends on the effect that the concrete would have on the compression capacity or the capacity.
Okay.
Professor, I agree with Eric. Point B is much more feasible.
Okay.
Sorry, I don't. I mean to say that I don't agree with Eric. I think we should use point D because if we change the design, we will need to bring it more metal and it will cost us more. But if we use the same beam, then the cost will drop.
All right, this makes sense. Also to confirm what you're saying here about item D or answer D, it says here for sure, and you don't have yet the crane weight. You don't have the construction life load. You don't have any of that. So how would you know that the beam size is gonna work? You don't have any confirmation.
We will have to calculate it.
Can it be like number 3? The contractor should not put an opening in the deck.
So how do you want him to do his business? Now he has materials. How can he bring it up? This is what we usually have in construction. In construction, you have a contractor who's going to be working, and before he starts to look at the drawings, you need to finish your design. And when you do your design, you don't know exactly what does he need to do during construction. This is why your structural observation is really needed when you have any construction. You need to be there. They need to come back to you if they're going to be doing any trains, any changes. You need to be aware of it to redo your analysis.
Sir, it says in the statement that the drawings were reviewed, signed, and stamped by a civil engineer. So it means that they must have calculated that that the beam W16 by 31 it can carry all the loads. So that's why I'm saying point D is the right one.
Yes, it is true that it is designed to carry all the loads, but not construction loads, because they know it can support standard construction loads. But when you have a crane, how would you confirm this? A crane is very specific thing that you put in a specific location, and the engineer at the beginning didn't know about it.
Doctor, does that mean that we have to consider the crane as part of the live load during construction? Like it's going to be sitting on top of our steel structure?
Maybe it's going to be sitting on the floor, which means all the way at the bottom at the foundation level, and maybe partially sitting on the steel beam, right? And it means that you're going to have non-standard structural life load, because if the crane is going to be happening at this location, it means that the material is going to be stored right next to it. So you need to figure out all of the loads, right? Contractor needs to provide his plan, what exactly wants to do, what type of load is going to be there at this location. Okay.
To me, it sounds like of course it has to be taken into account for the construction live load, but it seems very inefficient, at least cost-wise, to put larger pieces of steel just for the construction live load that will not be needed for the regular live load of the design.
In many cases, when you have a situation like this, you can just short the beam. So you come in the middle of the beam and then you put a post, temporary post. And once you're done, you can just take it out, if this makes sense.
Yes.
So let's say the beam is span at 30 feet, then you come at 15 feet, you put a post there. So you cut the span into half.
Yeah, that sounds about.
Yeah, but something needs to be done. You cannot just ignore it and say, beam is good, I don't really need to do anything, and the contractor can just proceed.
if we add a post, then it will be a continuous beam, and the moment at the supports will be on the top, and the concrete will not be effective to take it.
This is correct, but it's gonna be a new design for this beam.
Yeah, new design.
It's gonna be something that you need to run by the engineer. If you are working with
Yes.
a contractor, you need to run by the engineer.
Yeah.
Just ignore it.
If we change the beam, it's gonna affect the plume space below it, and every like pipe and mechanical hangers and everything will be disturbed.
Yes, you need to look at it. This is absolutely correct. All right, now before we proceed here with this tension member, I posted this already. And I wanna mention something about the homework that's due by end of today. As long as get be within today, it should be fine. I'm gonna open the deadline to the end of Sunday. And it's gonna be only at this time. So for any other homework or quizzes or exams, we're not gonna do this. I want you guys, for every one of you, to check carefully the deadline for submitting the homework or a quiz or an exam. If you didn't do it on time, I'm sorry, you're not gonna be getting a grade for it. Are we good?
Yes.
When is the quiz due?
There's no quiz yet, but I'm just talking here, generally speaking. Deadlines, please, needs to be respected. If you submit after the deadline, will not be accepted. And please do not send it to me in an email. There's a method to submit your homework. All right.
Professor, we submit the homework on Canvas, correct? Will you accept a blank sheet of paper just written in
What do you mean submitted on campus?
the homework?
On Canvas, yes.
Yes. Okay, great. And another question is, do you need us to do use engineering paper or some kind of lined or grid paper?
You can type it, or you can do any paper as long as your handwriting is very clear to me, is legitimate.
Okay. All right. Thank you.
Because I really have problem with the handwriting, especially when it's gonna be very fast, not clear, numbers are not clear, and I'm sorry, because I'm not gonna be able to grade it for you guys. And okay, if I'm unable to read the number, I'm gonna consider it to be wrong.
Okay, thank you so much.
Thank you.
Professor?
Yes.
So what was the answer for the last example?
Oh, the answer is gonna be B.
B?
Yeah.
Okay.
As we're saying here, contractor needs to go back to the engineer. This is gonna be like in the best practice, this is what happened. Contractor needs to provide a plan showing exactly what he wants to do in terms of the penetrations, the location of the equipment, and the storage location of the material, and expectation of the load intensity and location. Now the engineer needs to take this plan and revise his design. A simple option that usually a contractor would propose is to shore the beam. But if shoring is kind of impossible because you have other stuff running down below it. In a case like this, maybe the beam size needs to change. So the thing is, we don't want contractors just to proceed and do any changes during construction and have a disaster out there. A collapse or failure, or someone's gonna get killed or whatever, right? We don't want this to happen. So it's gonna be very important when it comes to structural design, then the engineer is gonna get involved for the construction life load. It's gonna be one of the critical items that usually ignore.
Okay, thank you. And is there a way to avoid this process after the engineer designed it? Like
yes, yes. Usually this is the case. After you do a design, construction starts. Now the contractor is gonna be taking your set of plans, and now he's gonna be planning where to put the crane and where to store the materials. Once he figures this out, he needs to run by you. Just to prove that nothing is wrong in your design, that nothing is going to be collapsing.
Okay, thank you.
No problem. All right, you guys, you have this tension member slide set. Now, this tension members, we usually use it when it comes to braces, truss members, and this kind of members that we have in the structural steel. All of these equations, you can see it in the EGCE 360-16. There's a chapter about tension members. It's so simple. You are going to see the exact equations. The strength for a structural member in tension is going to be the smaller of the result of these two equations. So I'm going to be taking this equation 2.1, run it first, and then do also equation 2.2 and see which value is smaller of the two and just use it. This is unlike when I have a demand like in the previous slide set. When I have a demand, I have two loads. One of them was 1.29 kip per foot. The other one was almost 2 kip per foot. And that's I'm going to be using the larger of the two. Now, when it comes to strength, I'm going to be taking the smaller of these two. Each one of these two equations is going to be based on a certain mode of failure of the structural member in tension. The first one here is going to be based on the tensile yielding. Now, you'd like to control the yielding of the member. So you say here, phi Tn, which means the tensile strength of the section, is going to be equal to a phi factor of 0.9 multiplied by the yield strength multiplied by the gross section of the member. Now it's kind of tricky. How about if the member has some holes? Should I consider the holes here? When it comes to A sub G, I'm going to say no. You do not consider it. It's just the gross section member. And the other one is going to be about tensile rupture. This rupture, if you like to avoid rupture, you need to design the member for a phi factor of 0.75 multiplied by the ultimate strength multiplied by effective cross-section area. Now, effective cross-section area of the member, of course, is going to be different from that for the cross-section area of the member. So, okay. Sounds simple. It's going to be two simple equations, but now I need to learn how to use it with different members and different situations. Yield strength, you guys, you are aware of it, you are familiar with it, you understand it. For ASTM A36, it's going to be 36 KSI. For the ASTM 572 or 992, like the one for W shapes and certain shapes, is going to be 50 KSI. The other value for the rupture is going to be the ultimate strength, F sub U. For the same A36, usually it's going to be 58 KSI. And for the 992 or 572, it's going to be 65 KSI. So if you have the material, you can either go back to the table that we went through in the previous slide set, or you can just take it from here. So I decided to provide here just for sake of discussion and to make it in the same slide set of the tension members. A sub G indicates the cross-sectional area of the member. The effective net area is going to be equal to the net area after we subtract the holes multiplied by a factor called U uppercase, like this. So it's going to be U times A net. So what is the net area? Net area is going to be equal to A gross subtracting all the cuts. Like if you have some holes, you need to subtract that. The shear lag factor, which is this U, is going to be taken from table D 3.1. This is in chapter D of the 360, of the EGCE 360 from the steel manual. All right, let's see about the holes, what happens, what type of holes you expect to have in the steel members. The hole size here is going to be based on the bolt size. If the bolt size is ½ inch, you cannot have the hole also as an ½ inch. It got to be different. We have something that we call here standard hole. It depends, of course, on the type of connection. We have standard holes, oversized holes, and then we have slotted holes. If nothing was mentioned in the problem, you're going to be doing it as a standard hole. Don't do oversized hole. Oversized holes is used only in column paste plates. Otherwise, don't do it. And not all columns. It's giving gravity columns. If the column is supporting wind load or seismic load, do not use oversized holes. It has to be standard holes. So generally speaking, let's just stay here with the standard holes. So if the bolt size is ½ inch, the standard hole is going to be 9/16. ½ inch means 8/16. Generally speaking, I can just go here at the bottom. You see here the diameter, take the bolt diameter plus 1/16 of an inch. You cannot have it of the same size. Otherwise, you cannot put the bolt in. So in this table here, taken from the code, you're going to see here the bolt diameter and the standard size diameter. If you forgot how to get to this table, just take the bolt size plus 1/16 of an inch. It should be fine. Now the U factor. If you remember that I have here two things. I need to do the cuts. Also, I have this U factor. U factor is taken from this table. Look at this U factor. This is going to be the very common thing that you're going to see, or maybe one of these two. Look at this. Here's a steel angle, or WT. Or we have a W section with two plates, top and bottom. Or two plates to the side of the web, of the beam. The factor U here is equal to U equals 1 minus X over L. What is this X bar over L? We figure this out. Look at this X. X is to be the distance from, you see here, you have a plate and an angle, right? They attached to each other. X is going to be the distance from the CG of the angle section to the interface between the plate and the angle. Look here at this X bar. It's going to be the distance from the plate to the center of the W section. Look at this L. It is going to be equal to the weld length. How about here? Is going to be the welded in the other direction, or it's going to be the distance between the first and the last bolt? We're going to see some examples here to determine X bar and L, and be sure that we know how to use them in the right way. Here's one example. As it says here, I have the angle section. Here's the size. Here's the steel material. I have 3 bolts, ½ inch bolt. In this case, L is going to be equal to 8 inches. The X bar, I need to do it based on this analysis. Excuse me. I'm going to show it here to you on this slide. I guess this is going to be a good stopping point. It's already time. And you guys feel free to ask me questions or stay with me online if you have any questions to ask. For now, please go ahead and sign your name to leave out.
Thank you, Professor.
All right. Thank you.
Okay, Professor, just to confirm, you changed the due date for the homework to Sunday?
Yes. I'm gonna.
Okay. Okay. Yeah, on Canvas it still says today at the night.
No problem.
Professor, I just had a quick question.
Yes, please.
No, actually, never mind. I just found the answer for that. Thank you.
Question about? Maybe someone else has the same question.
Professor?
Yes.
So I just have a quick question about so in the example that we finished in the previous slide set, you said that there's going to be a hole in the concrete metal deck, right? So we can put a crane to lift stuff up, correct?
Yes.
After the entire construction is done, how would you patch that up? Would you just weld the metal deck back together and then pour on top of it?
Yes, you can do this.
But then would you have poured the rest of the floor, or would you pour the entire floor together?
You can either just leave this opening and pour the entire floor if it's going to be a small piece of the floor, because you don't want to delay all of
Right.
the in this location. So you can have some rebars to stick out. You can dowel in and you can roughen the surface. And the interface between the existing concrete and the new concrete, if you like. And then you put the metal deck and then you pour the concrete. You can do
Okay. And the metal deck would be welded together on top of the...
You can weld it, or you can use fasteners, like
Okay.
in welding to the steel framing below.
Got it. Okay.
Yeah, it needs a design. You cannot just ignore it, but it needs a design, and you can put it back the way you want.
Right, and then yeah, you could just pour the concrete and use what you said, dowels or something to connect the old concrete to the new concrete.
This is absolutely correct. Yes.
Got it. Okay. Thank you.
No problem.
Oh, and well, can I elaborate on one more thing though?
Yes. Go ahead.
Because you said that the answer would be B, right? So if the new section, if we couldn't shore it and the new section was larger than the existing beam, wouldn't that mess up too many things in the floor, you know, across it with the height if you have a bigger section?
Well, the section, let's say that you have W16 by 31. I
Right.
make it W16 by 40. So the depth
Okay.
is almost the same.
Okay.
I may just weld the plate at the bottom of it. Or I may weld the WT, a very small WT, 2-3 inches only. Or maybe make it W18 by, still maybe make it work.
Okay. So you would, but you would only mess with that singular beam, but not touch everything else. That's...
Yeah. Yes. Unless other stuff is going to get affected by the hole, you know?
Okay.
You never knew exactly where the hole is going to be. What is the plan of the contractor? What's his plan?
Right.
In construction. So what I'm trying to say here, your involvement is going to be very important to redesign the beams.
Right.
Checking.
Would the addition of extra beams to reduce the weight on that specific beam, you know?
Yes, you may do this.
Okay. Okay.
Yeah.
Just seeing what the options are.
Yeah.
All right. Sounds good. Thank you very much.
No problem.
Professor, I wanted to check in the beginning when you called my name, my Zoom was glitching in and out. So I just wanted to confirm that to see what you marked me in the beginning.
All right.
Yeah. Awesome. Yeah. Okay. Thank you so much.
Have a good night, doctor.
Good night. Good night.
Bye, doctor.
Yes. Good night.
Good night, doctor.
Good night. Good night, guys.
Have a good night, doctor.
Good night. Good night, everyone.